All right, we've previously talked about subatomic particles and how the proton and the neutron are in the nucleus of the atom. And so far, all we've said about the electron is they're outside of the nucleus. And so what we want to talk about now is a little bit more about the location of the nucleus, or not the nucleus, of the electron. And unfortunately, all we can really, in the end, tell you is where the electrons probably are because they're moving around. And we can just say where they're most likely to be found. And to define the area in which they're found, we'll look at what are called quantum numbers, right? And so and if you think about these quantum numbers is almost like an address telling you where you're going to find the electron and which way they're going to be spinning when you find them. Then these set of quantum numbers define an address, or and we may go over another analogy later. But the principal quantum number, which is also known as the shell number, defines the location of the energy level. So remember that the electrons within an atom have can be at different energy levels, and those are quantized, so they have to be at specific levels. They just can't be anywhere. It's not a continuous array. It's more like steps. And so this principal quantum number n tells you at what energy level they are. Once we know what energy level they're at, then we can look at the angular momentum quantum number, and that tells you the shape of the orbital. And so the angular quantum number, L, can range from 0 to n minus 1. So orbitals with the same value of L form a subshell. So we have shell and then a subshell. And if we dig down a little deeper, the next level would be the magnetic quantum number, which specifies the z component of that orbital and really tells you its orientation in space. So in the x, y, z plane of three-dimensional space, it gives you the orientation. So these first three will give you kind of the location. It'll tell you at what energy level it is with that subshell or shell looks like and how it's orientated in three-dimensional space. This final quantum number, the spin quantum number, tells you about the electron that's at that location, and that electron can either be spinning plus 1/2 or minus 1/2. So through this series of numbers, it can tell you exactly where we would expect to find that electron and which way it would be spinning when we do find it. So at the first and lowest energy level, n is going to equal 1. So n equals 1 at our lowest energy level. So then if we start saying, well, what kind of shapes do we have from our orbitals at this lowest energy level? If we look at the possibilities, L has to equal up to n minus 1. So if n equals 1, L equals 1 minus 1, which equals 0. So the only value possible at energy level 1 would be for the angular momentum quantum number to be 0. And if L equals 0, it's what we call an s orbital. And the s is for spherical. So what we have is a sphere in three-dimensional space where we're most likely to find the electron. So the electron is within this spherical orbital moving around. Now, since this is a sphere, its orientation doesn't really matter in three-dimensional space, right? So if we had a sphere and we rotate it this way, it's symmetrical in all directions. So it doesn't really have a difference in the x, y, and z plane. It's the same in the x and y direction and in the z direction. So there is no magnetic quantum number, so there's no z component to worry about here. And so within this orbital, we can have two electrons. One could be spin up and one could be spin down. Once we get to the next energy level, so we've moved from the lowest energy level to the next one up, then n would equal 2. And when n equals 2, then your angular momentum quantum number can either be n or 2 minus, it can be 0 up to n minus 1, so 2 minus 1 is 1. So we could have a 0 and a 1 here. So we can have s orbitals, because that's when L equals 0, and we can have p orbitals, because that's when L equals 1. So we've already said that the shape of the s orbital is spherical, but what about the shape of the p orbital? So the p orbital actually is this dumbbell kind of shaped orbital like that, and you actually have three different shapes. So you have another one coming like that in the other direction, and then you would have one, and it's hard to draw, but you'd have a third one that's actually coming out of the plane of the board. And so then you end up with a magnetic quantum number where you have these 3 orbitals, right? And so if we kind of take them apart, what you end up having is a p that's in the x direction orientated in space. Then you have a p that's in the z direction orientated in space, and then you have one that's in the y direction, which I guess is going to be coming out towards you. And so once you get to this p shell, then you have 3 different orientations with your magnetic quantum number. And as the numbers keep getting larger, then once we go to the energy level of 3, then this L can equal 0, 1, or n minus 1 then becomes 2. And so if L equals 2, then you have d orbitals. And there are 5 d orbitals, and their shapes are beyond me to draw. But then you would have 5 different orientations in orbital space. So at the d level, you would have 5. And then as you move up, you would continue to have more. So at the d, you would have one that's orientated. You have a dxy, a dxz, a dz squared, a dy squared, and a dx squared minus y squared. And so you can have 3 different orientations in space, and each one of those could hold a pair of electrons, and one electron would be spin up and one would be spin down. So if we think about these quantum numbers as giving us the location of the electrons in space, let's imagine that we had a hotel that looked like this, and so we have a first floor, a second floor, and a third floor. Right, and those would be our energy levels. Think about it taking less energy to climb the stairs to get to the first floor. If it takes more energy to climb up to the second floor, so it's a higher energy level. It takes even more to climb up to the third floor, so it's a higher energy level. So based on our rules on the first floor, we only have one type of room. We have a single room, right? And that room has one bed in it because it's a single room. And so our principal quantum number, we're at the first floor, we're in a single room, there's no differentiation with orientation in space. And what are our people doing in there? One person has his head on this end of the bed, and the other person has its head facing the other way, and so they're opposite, just like plus and minus a half, like the electrons would be. Once we move up to the second floor, then we have 2 choices of rooms. We have this single room again, which is like our s orbital, and then we have a larger room, like a suite, but it's a 3-bedroom suite, so you have 3 different beds in there. And this is like our p orbital, where you have a px, a py, and a pz. So that would be the orientation in space, and I should have drawn those spaced differently. And then in each of these beds, we could have 2 people, but they would have to be facing the opposite direction of each other. Very odd rules in this hotel, right? And so once we climb up to this third energy level, then we have even a wider choice of rooms. So we have the standard room we're familiar with the one bed, and then we have our larger room with our 3 beds. So we have a 3-bed suite. But then I guess the hotel needs to have a little expansion on it. Then we have even a larger room that is like a 5-bed suite. Right? And so as we get to higher and higher levels of the hotel, they're higher in energy because we have to walk higher, but then we end up having a wider assortment of rooms to choose from. We still have our S orbital, and then we have our P suite here, and then we have our D suite. So remember, we have a PX, a PY, and a PZ because all of these beds are facing different ways in space. And the same thing with D, we have the 5 different ways that those beds could be oriented. And then if we went up to our 4th floor, then we would get a further expansion where we would move into our F orbitals.